Quiz 0.1, Problem 1. Which of these define functions? So in every case here, we're thinking about this as relationships between inputs and outputs, where, for instance, with the first one, it's saying the input is 1, the output is 2. It's saying when the input is 2, then the output is 3. When the input is 3, the output is 4, and when the input is 4, the output is 5. Right? We can think about that as a bunch of different ways. We could actually draw this as a set of points where we have the point 1, the point 2, the point 3, the point 4, and it gets mapped to the point, I guess each one of them is 2, 3, 4, and 5. And we could think, okay, 1 gets mapped to 2, 2 gets mapped to 3, 3 gets mapped to 4, 4 gets mapped to 5. And we could see, right, in every one of these cases now, this is a perfectly good relationship. There's a perfectly good rule. Every one of these has a domain, and that's simply just the set of all of the first inputs. So in the first case, the domain would be 1, 2, 3, and 4 all together as a set. The range in the first case would be 2, 3, 4, and 5, this group as a set. And that's the case with all of these. So the only question really comes down to, for every one input, do we get one and only one output? And in this case, especially after drawing it out like this, you could see, like, yeah, 1 only gets mapped to 2. There's no other number that it goes to. 2 only goes to 3. 3 only goes to 4. 4 only goes to 5. You don't end up with anything crazy like, say, this, where 1 goes to both 2 and to 3. There's nothing like that. So this is pretty straightforward. And as a matter of fact, the way I think about these, if I'm going to be presented with this information in this form, with sets of ordered pairs, right? Sets of input and output values, what I'm going to look for is, well, is every input value only defined once? And here I could just say, yep, there's only 1 here. How many times is 2 the input? Well, 2 is only the input once. 3, yep, the only time 3 is an input is 1 time. 4, yeah, same here. So 1 gets mapped to 1 and only 1 number. 2 gets mapped to 1 and only 1 number, and so on, right? So yes, this is a function. By definition, it's a function. Okay, the second one, same kind of reasoning here, right? I'm just going to look and see. Now you notice the first one I wrote, those are all nice and in order. We don't have to write anything in order. There's nothing saying that we had to write things in order, right? So there's nothing wrong with this. We have a group of inputs, 4, 3, 3, and 1. Oh, maybe there is something wrong with this, right? So let's just take a look at this. 4 gets mapped to 2, no problem. 3 gets mapped to 3, no problem. 3 gets mapped to 2. 3 also gets mapped to 2. So 3 is going to 2 different places. 1 is going to 5. Let's see how this would look if we were to write this out. We have 4, 3, and 1 as inputs. We have 4, 3, and 1. And the outputs are 2, 3, and 5. 2, 3, and 5. The first one says that 4 gets mapped to 2. Okay, the second one says that 3 gets mapped to 3. Third one says 3 gets mapped to 2. Finally, 1 gets mapped to 5. And we can see that's the problem right there, is 3 has, we have 1 input that has 2 outputs. That is not good. So this one is not a function. And I also said to explain why when it's not a function. Well, we have 1 input, 3, that has 2 outputs. That's enough to say right there. 1 input has more than one output. Okay. Okay, the next one. I'm going to look at this. Okay, we have a set of input values, set of output values. Looks good. Okay, 2.01, 2.02, 2.03, 2. Now you see I was trying to trick you. I wanted you to say, oh, yep, that's the same as that, but it's not. It's slightly different, right? We could see these are all unique input values. So then there's no way that one of them can get mapped to two different things. So in this case, this is a function. Not the same reasoning we set up here, right? The numbers look a little bit different, but ultimately it's the same principle. Every one input has one and only one output. Now, let's look at part D. 2.01, 2.02, 2.03, 2.001. It's exactly what we had before. I'm done. It's a function. It is a function. You're going to say, but wait a minute. It's the output's always 2.02. Doesn't matter. Doesn't matter. The output can be 2.02 every time. It does not matter. That has nothing to do with the definition of a function. Let's see how this is a little bit different than the previous case. We have 4 different inputs. There's 2.01, 2.02, 2.03, 2.001, and we have one output, 2.02. Every one of them gets mapped to that one output, but there's not any one of them that goes to two different places, right? That is the key with functions. For every one input, you get one and only one output. One input, one output. One input, one output. They could be all the same output. That's fine. Perfectly good function. Just as long as this one doesn't end up going to two different places. So that's fine. It's a function. Okay. Part E. Now, as inputs, we have colors. We have red, green, blue, and white. Our outputs are Greek letters, beta, gamma, alpha, delta. And again, really don't have to use my brain beyond, okay, red, green, blue, white. Those are all unique inputs. Even if they all went to the same letter, even if it was red beta, green beta, blue beta, white beta, the whole way, just like before, that's fine. That's a perfectly good function, okay? But in this case, they're all going to unique letters, whatever, it's a different kind of thing. We're just interested to make sure that one input gives me one output. So one input, I don't see it anywhere else, good to go. Different input, it's nowhere else, good to go. Blue, different input, nowhere else, good. White, it's the only place white shows up, so we are good. This is a function. Okay, now, what about this guy? F. We have 2 to the third and 2, 3 and 3, 2 and 3, 8 and 5. Now, immediately when I look at this, I'm like, oh, we have 3s, and look at that. Oh, the outputs, oh wait, no, we can have the same output. The same output's fine. Then I see, oh yeah, these have different inputs. Okay, so that's not really a problem there. So now I'm gonna look and say, oh wait, now what is 2 to the 3? Well, 2 to the 3 means the same thing as 2 times 2 times 2, 3 times. So I have 3 2's there. So 2 times 2 is 4, times another 2 is 8. Oh, it looks a little bit different, but that's the same as that number right there. And so what do we have? Again, I just want to draw this out. We don't have to draw this out. Right now, we're pretty much done, but I just want to be explicit, right? In the first case, we have an 8. In the second case, we have a 3 as an input. Third case, we have a 2. In the last case, we have an 8. Oh, we've already written 8. 8 is right there. Same input 2 different times. Well, let's see what the outputs are. 2 and 3, 5. So 8 here gets mapped to 2. 3 here gets mapped to 3. 2 here gets mapped to 3. No problems. We have a collision on this side, but that's fine right now. But now 8 gets mapped to 5. And so by definition, It's like, well, we have an input that has more than one output, so this is not a function. All right, last one. Oh, hey, that looks almost exactly the same as the first one. Well, it's not a function, right? I mean, I'm looking through here and I'm seeing we just learned that's 8. There's 3, there's 2. Oh, 8's another input. So it's not a function, right? Wait a second. Let's do this again. We have 8 as an input. We have 3 as an input. We have 2 as an input. Back to 8 as an input. Let's see what the outputs are. 2 and 3 and 2. Okay, we're good to go. In the first case, 8 gets mapped to 2. Input 8, output 2. 3 gets mapped to 3. When you input a 3, out comes a 3. Plug in a 2, out comes a 3. That's fine, right? Go to there, but they come from different places, so it's all right. Now, it says that 8 goes to 2. Oh, there's nothing wrong with that. That's perfectly fine. It's just a redundancy in it. So that was deliberately tricky, right? I wanted to throw that in there, but technically there's no problem. I just happened to write it twice. And that's one of the things about when you write something in set notation, right? When you have repeats, 1, 2, 2, 3, say, this is the exact same thing as the set 1, 2, 3. So that's kind of what's going on here. I was deliberately being tricky with these last two, but we could see that there's actually no problem. I've just been redundant, and so the last one is a function. Okay, quiz 0.1, problem 2. I've drawn 6 different graphs, and I ask you which ones of these define functions. And we understand that this is a relationship between inputs on the x-axis or the horizontal axis and outputs on the y-axis or the vertical axis. And so we have a rule or a test called the vertical line test, right? And I ask you that if something's not a function, to explain why. Now, if you said because it didn't pass a vertical line test, that's cool, that's fine, but as long as you know what that means. So I'm gonna be getting into that. So, okay, let's look at the first one. And we're thinking, okay, vertical line test well, it says that if we draw a vertical line that at any point or any place along this function, it would intersect this line only once. What do we mean by that? Well, that means is for any one input, right? So like let's say when x is this value right here, we get, that's my output right there. A couple more. When this is my input value for x, it says that my output value is that guy right there. Similarly, when this is my input value, that's my output value. This is my input value, that's my output value. So drawing a vertical line, in a sense, is like saying, well, for any one input, it only hits one time. It's like saying that there's only one output for that right there. And that's what we are seeing with this function right here, that we never see it kind of going back over on itself. There's not a vertical line I draw where it touches in two places. It always touches only once. So then for every one input, there is one output. For every one input, one output. And so yes, this is a function. Same thing with B. If you notice, and I'm not sure if we've gone over this in class yet or not, but this is actually a parabola that I plotted, and it looks like this. This kind of just looks like a bunch of parabolas just kind of joined together, right? And in every case, if you're looking at any one part of it, it's like, oh yeah, you can see that's like a parabola. It does what we just saw before. Any one input goes to one output. Any one input goes to one output. There's no place above or below that hits it anymore, right? And we do that for, you could just see that in every case, that's going to work. In other words, it passes the vertical line test. Any vertical line I draw will cross this thing only once. Said differently, any one input has only one output. That's what it is to be a function. That's a function. Moving on to C, though, it's pretty obvious that that's not the case. One way of saying that is that it does not pass the vertical line test. If I draw a vertical line, say right here, we get two places where it touches. It would touch here and here. That means that when this value of x is the input, we get these two values of x of y as the output. Same thing here. When that's my input, I get this and that as an output. Said differently, the vertical line test fails right there because it hits it in two places. So this is not a function. And again, you could say that because there are inputs that have more than one output. You can say that because it fails the vertical line test. It means the same thing. As long as you know that it means the same thing, we're cool. Okay, how about D? Well, this one's pretty obvious, right? Again, I can choose any point. How about that point? That input gives me 1, 2, 3, 4 outputs. It's already failed. We could just stop right there, but let's just look at a couple other places. This also gives me multiple outputs. Said differently, a vertical line drawn anywhere would intersect it at this point 1, 2, 3, 4 times, right? This is not a function. Not a function. Multiple outputs for one input. Okay, E. Pretty straightforward. There's this sharp little corner right there, but that's not a problem for it being a function. Again, vertical line test, anywhere along here, it should pass, right? I'm seeing only one place where it's going to go. There's this weird corner, but that's not a problem. It just hits it at one place. Said differently, for any one input, I get one output value. When I plug this x in, I get out that one y value and no other y values. That's true for everywhere that it's defined. That is everywhere that we've seen it, right? So this is a function. Okay, the last one. Now, if I would have only drawn that right there, that would be fine, right? That's just a line. A vertical line would only hit it one time, right? The problem comes when we go over the y-axis, or it's actually at the y-axis, although I doubt you could see it on the paper, right? But right there, that's where we start running into problems, where I plug in, say, a 0, and I get that as an output and that as an output. Plug in this number right here, I get that as an output and that as an output. For one input, I get more than one output. Said differently, the vertical line test would fail because it would cross it in more than one place. All means the same thing. This thing is not a function. Problem 3, graph these lines, write their slope, and then in part G, I say determine if they're functions or not. Okay, so first off, whenever we're graphing a line, whenever I'm graphing a line, I like to get my line into this form. Y equals mx plus b. This is called slope-intercept form, right? Where whatever number that is, we call the slope. Whatever number that is, we call the y-intercept. Let's think about why that is real quick. Like, and this is going to be important. If we think of y as a function of x, which is a really nice thing about writing it like this, getting y all by itself, is that now we can think about this as a relationship between inputs, which we call x, and outputs, which we call y. And when we go to graph this, okay, we always call this horizontal axis here, we call that the x-axis, and we call the vertical axis the y-axis. So in other words, the input axis and the output axis. And so whenever you cross the y-axis, and I don't care, this doesn't have to be a line, this could be anything that crosses the y-axis. It could be up here, it could be something down there, it might be a line, it could be anything. Anything that crosses this y-axis does so wherever x equals 0. That is, the only way to be on the y-axis is when your x value is here at 0. X can't be 1, x can't be -1, it can't be 5, it has to be a 0. Then you're on the y-axis. Similarly, if you're on the y-axis, your x has to be 0. Okay? So we could say, what's nice about this is, if we want to find out where does this line cross the y-axis, we have some line that does something like this, we don't know, we just need to know where does it go through here. Does it go through here? Does it go through here? Well, if you're on the y-axis, your x value is 0, right? So, if your x value is 0, what is your y value? Well, let's take a look. If your x value is 0, I'm plugging in a 0. M times 0 is a big fat 0. All you're left with is b. So when your input is 0, that is when your x value is 0, your y value is equal to b. And that's why we call it the Y-intercept, because it goes through at wherever number that is. If that's like a -5, it would be down here at -5. If it's a +2, it would be up here at a +2. That's why it's called the Y-intercept. It's much more important to think about the relationship between x and y. That whenever you're on the y-axis, your x value must be 0. Similarly, whenever you're on the x-axis, your y value has to be 0. So we're going to use that a lot. All right, now, y equals -2x. So, part A, y equals -2x. It's already in the form that we're looking for, right? Here's my m. And what's my b? Well, it's not written, but it's a big fat 0, right? It's not written. We can always add 0. It doesn't change anything, but that's the y-intercept. It must go through at 0. It must have a slope of -2. All right, so I found my slope. In fact, it's going to be the first thing I do, because it's one of the things we have to do. We have to identify the slope. And now we just got to draw this guy. Okay, so label my axes, x and y. So another thing we could have done, instead of trying to identify, oh, there's the y-intercept, because, it never showed up, right? It's never there. You could, if you don't know what to do, just say, well, what happens when x equals 0? And you plug in a 0. -2 times 0 is 0. So you get that y equals 0. So when x equals 0, y also equals 0. So we got our y-intercept. Now we could say, okay, a negative slope. Every line, there's only 3 possibilities with a line. Either it's a horizontal line. Well, I guess there's 4 possibilities. It's a horizontal line. It's a line that goes up like that. It's a line that goes down like that. Or it's a vertical line. There's really only 4 possibilities. If the slope is negative, that means it is a downward facing line. And so there you go. Now it goes through both axes right here at 0. And so I'll label 0, and that's all I'm looking for. I don't care if if the rise over the run is actually 2. If you had drawn it like this, where it's certainly not equal to -2, I don't care. It's qualitatively accurate as long as you show that it's going through here at 0 and you label it as 0, we're good to go. Part B, y equals 5. One way of thinking about this is to say, well, if I want to put this in the form y equals mx plus b, see that there's no x there. And kind of like with the last one, right, it's like, well, there's no b here, so we called it 0. Similarly, the only way that this could equal that is if m is equal to 0. Like that. And then we get, okay, y equals 5, so that equals 5. So it must be the case that b equals 5. And so then I know that that's my y-intercept. Yeah, okay, that's one way of thinking about it. Oh, and we would also know, well, then my slope right here would be 0. So I would say m equals 0 is my slope. Check, okay, because we have to identify that anyway. But another way of thinking about this is to say, okay, this is a function. And what this function says is that it's a relationship between x and y. I'm going to go ahead and write it out. Y of x equals 5. So when x is 0, I plug in a 0 and I get out a 5. Okay, when when x is 1, I plug in a 1 and get out a 5. Okay, when x is 2, I plug in a 2 and I get out a 5. In fact, all x values that you could plug in, sounds weird, right? But it's y is equal to 5 for all of those values. And so really, this is just a horizontal line, like that. Then we could say, well, what's the slope of that line? Well, slope is the rise over the run. Okay, so I'm thinking slope is rise over run. But it doesn't rise, right? It always stays at 5. I don't care how big of a run you take, right? We could go from, say, from 0 up to pi, and it's 5 here, it's 5 here. So we could say, well, what's the difference between 5 and 5? 5 minus 5 is a big fat 0 over, I don't know, pi minus 0. It doesn't matter how big or small that is. But 0 divided by anything is still just 0. So then we could say, well, then the slope is just 0. So a couple different ways of thinking about it, but ultimately it should be pretty straightforward. When you say y is equal to 5, you're just saying y is a constant value. It's always 5. And so we should just have a straight line right there at 5. Only thing you really have to label is where it crosses right here at 5. And you're done. C, y equals 2x plus 3. You can see it's already in slope-intercept form. Right, we have the slope right here, so I'm just going to go ahead and write m equals 2. That's my slope. Done. Now, the y-intercept is 3. Another way of saying this is that it goes through the y-axis whenever x equals 0. I plug in a 0. 2 times 0 is equal to 0. The output must be 3. Okay, so I'm going to go ahead and draw a 3 right there. Now, the way I do this is I'm going to say, well, is this a positive or a negative slope? Or is the slope 0? If the slope is 0, it would be straight across. It's not. It's 2. It's positive, so it means we're actually rising. We're going up. Things are getting bigger as you put in bigger values of x. Another way of saying it is we are running uphill as we go this way. We're running uphill. Okay, are we done? Well, no. Right? So this goes through the x-axis. Right there. But where is that? Right? We have to label that. So, same way that I think, like, same way that we were just talking about, I love to think about these as functions. Right? So I'm going to say y of x is equal to 2x plus 3. We're going to say, okay, now this is a relationship between the y outputs and the x inputs. And now we're trying to find out where does it cross the x-axis. And we could say, well, there's a relationship here, right? Or, well, first off, we know anytime you are on the x-axis, your y value has to be 0. So in other words, the output value, the height, the y value, has to be 0. So I'm going to say then the output of this is 0 when what? And we're kind of asking, it's like, I'm going to plug in some value of x. I'm just going to call it x. And when I plug that in, I do this, and then my output, my height value here is a 0. That's what that means. So now I have 0 equals 2x plus 3. Trying to get x by itself, right? That's the number I need to find. So I'm going to say, okay, x gets multiplied by 2. Then he gets 3 added on. So I undo the 3 first. So I'm going to say, to undo addition, I subtract. That gives me a minus 3 equals 2x. Okay, now x gets multiplied by 2. To undo multiply by, I divide by. Okay, so now we have x equals negative 3 halves. All right, that should be that point right there. So negative 3 halves is there. And we are done. That's what I expect. Good to go. But one thing you might want to do, and in this case I feel pretty confident about this, but we could just double check our answer here if you're not certain. And this isn't just for lines here. This is for anything you do when you're graphing and you want to make sure you got it right. We could say, well, hold up. We just said that when I plug in this number, the output should be 0. So let's just check that real quick. I'm going to do that. I'm going to say, okay. When I plug in an x of negative 3 halves. So what is that? Y equals 2x plus 3. We're saying that when you plug in this value for x, you should get out a 0. Let's make sure that happens. 3 halves. Okay. That's a 2 over a 2. Another way we could think about this is like 2 times negative 3 all over 2. You could just look at it and say, oh, that cancels that, right? That's what happens there. We're left with a negative 3 plus a 3, which is indeed a 0, which is what you're looking for, right? Another thing we could do real quick, just to make sure we got this, is this says that when we plug in a 0, we should get out a 3. So if I plug in a 0, I can see pretty easily. I'm not going to go through all this, but yeah, 2 times 0 is 0. That goes away, and so y is just equal to 3. And that is what I'm looking for. Again, I don't care if it's pitched way up or way down, right? This is certainly not a slope of 2. That looks more like a slope of 1. I don't care, right? I would care if it were going down, and then it went through right here, and you called that point negative 3 halves, and I'm like, no, that's not a negative number. You're on this side of 0. That would be bad. But this is all I'm looking for. We don't need to measure anything. This is a qualitatively accurate graph. X plus y equals 1. Okay. My goal that I have in mind is to get this into the form y equals mx plus b. Right? Because I know how to deal with this. I don't know how to deal with that. That's a bit beyond me right now. But I have a good understanding of this, so what I'm going to do is change that thing into this thing. And the important point to notice is that this y is all by himself, right? So when I look at that, I think, how do I get y by itself? Well, what happens to y? Y gets added by x. So to get rid of x, I'm going to need to subtract x from both sides. That gets rid of that, leaving me y, which is what I wanted in the first place. Now we have a minus x plus 1. Now, you might have written that as 1 minus x, which is true. That's absolutely the same thing. But if you did that, I mean, it's not too hard to see what to do, right? It's just sometimes we get really caught up in what we're doing, and then you're like, wait, this is supposed to be like that. Where's my m? I don't know what's going on. And so I just wrote it like that. Anyway, here's the point now. We have to find the slope, right? So that negative x is the same thing as negative 1 times x plus 1, right? So I'm going to say, okay, my slope, m, is equal to negative 1. Okay. Graphing it. We have the y-intercept. It's right there. In other words, there's x, there's y. When I plug in a 0 for x, my y is equal to 1, and so I'm up here at 1. And I know my slope is negative. I have a negative slope, so it's going to go down, generally, like that. Okay. I see that it crosses the x-axis. When it crosses the x-axis, that means that y is equal to 0 there. And we have a relationship between x and y. The output is 0 when the input is what? That is what we're trying to find out. I'm going to plug some number in here. I don't know what it is, but the output is going to be 0. So 0 is my output, minus x plus 1. A couple ways we could do this. I'm going to go ahead and add x to both sides. And we get x equals 1. So that guy right there should be a 1. Just going to double check it. Plug in a 1. Plugging in a 1, I get minus 1 plus 1 equals 0. Yep. Plug in a 0. Plugging in a 0 gives me a 1. So when x equals 0, y equals 1. That's perfectly good right there. X equals negative 3. Now, this one's tricky. At least it is for me. I don't know about for you, but for me it's tricky. And trying to think, well, man, what's the slope of that? I need to put that in some kind of y equals mx plus b. I don't even know where to begin with that, right? So what I'm going to do is draw it first. Sometimes we want to start with the equation first, and if you don't really know where to go, well then try something else. Maybe try graphing first and see what happens. That's what I'm going to do. I'm going to say, okay, when x is negative 3, we must be down here somewhere, so we're at negative 3. This says x is always negative 3. No matter what the value of y is, x is always negative 3. Right? So it must be the case that this guy is a vertical line. And indeed it is. Anytime you have x equals a constant, it's just a vertical line. So are we done? Well, no, we got to find the slope of this guy. Uh-oh. Rise over run. I guess I could use any rise I want. Maybe up here at 2 and 1. So, okay. Rise over run. rise is, well, I guess we're going to go from here to here, I guess. So going from 2 down to 1, so 2 minus 1 is the rise. The run, I guess in both cases it's minus 3. We haven't moved anywhere, right? Well, 2 minus 1 is 1. Negative 3 minus negative 3 is, uh-oh. Yikes. Let me just check something here. Yeah, there is no run, is there? Like, there's no distance in this direction. It's just a point, right? So it's like, how long is a point? Well, it's 0. It takes up 0 length. There's no length to that. So we have 1 divided by 0. Is that defined? No, it's not defined. So we could say then the slope is not defined. So if you said something like the slope is infinite, right? You have an infinite rise for any run. I'll allow that. That's cool. In fact, that's really creative. I like that. But more to the point is that we can't really define a slope for there, right? Because even if we tried, and it's like, well, what if your rise was from there to there? What if your rise was from negative 1 billion to 700 billion? It's kind of like, well, no matter what, I mean, you're going to get the same thing. It's kind of like the same thing as trying to divide by 0, which, hey, what do you know? Like, you don't really get anything that makes sense. And so, just as a rule of thumb, vertical lines have undefined slope. Part F, 2x minus 3y equals 5. Now I know what I want, right? I want to turn this thing into y equals mx plus b. It's a fancy way of saying get y by himself, right? So I need to get y by himself. There's a few ways I could do this. In fact, I'm just going to go ahead and do both of them. So one way is the very systematic way. I'm going to start by thinking about what happens to y. Right? There's my y. I want him by himself. So what happens? Well, first he gets multiplied by a negative 3. Then he gets a plus 2x added on to him. So the last thing that happens is a plus 2x. So we're going to minus a 2x from both sides, leaving me minus 3y equals minus 2x plus 5. Then I could say, okay, what happens to y? Well, y gets multiplied by negative 3. So to undo multiply by negative 3, I divide by negative 3. When I do that, I got to do it to everybody over here, right? So I'm going to go divide by negative 3, divide by negative 3. And I say, oh, well, the whole reason I did that was to get y by himself, and yeah, indeed, that cancels. Negative 2 divided by negative 3 is the same thing as positive 2 divided by positive 3x. Kind of just pulling that x out there. Now, positive 5 divided by negative 3 is the same thing as negative 5/3. That's one way we could do it. And that's the systematic way and stuff like that. But honestly, if I were doing this one, I probably would have looked at it like this. I would have said, well, that minus 3y, get rid of this. I would say, that minus 3y, I could get rid of it by plussing 3y to both sides. I'd say, well, plus 3y. And indeed, that gets rid of that bad boy right there. We get plus 3y plus 5. Now I got to get y by himself, and so now I'm back to that whole thing like, well, okay, y gets multiplied by 3, then he gets added to 5, and so about minus 5 first, and we get 2x minus 5 equals 3y. Then we say, okay, y times 3, we undo that by dividing by 3, do that to everybody, and hey, what do you know? You end up with this right here. So either way you do it, that's fine, right? Sorry if this is a bit too elementary, but I, just want to make sure we're clear. Okay, so we've changed this into this form. I'm going to get it out of the way here. I'm just going to rewrite it right here. Y equals 2/3 x minus 5/3. Okay, so we're going to graph it. So I need axes. Say here, here. There's my x. There's my y. Now, okay. Let's find the y-intercept. Plug in a 0 for x, and my output becomes. So in other words, when x is 0, my output is minus 5/3. So I'm going to go down here to minus 5/3 and label it. And then I notice, okay, we have a positive slope. Positive slope goes up. So up like that. Are we done? Oh, nope, crosses the x-axis. But we know that it crosses the x-axis when the y value is equal to 0. So I'm going to say when y equals 0, what does x equal? Now I'm just trying to solve this. I'm trying to get x by himself. So I'm going to add 5/3 to both sides. And we get 5/3 is equal to 2/3 x. Oh, I can do this a few different ways. Right, we could see this as like x gets multiplied by 2/3, so we need to divide by 2/3. It's one way of thinking about it. Or we could say multiply by the reciprocal, 3/2. That would kill that, right? If I put 3/2, that would also kill that. Another way is to just say, well, why don't we just kill that denominator? What could I do to get, like, I'm looking at this, and it's like, that's what's messing up my life right now. I wish I could get rid of it. Well, how do I undo divide by 3? Well, how about multiply by 3? So I'm going to multiply both sides by 3. That cancels that. I get 2x. That cancels that. I get 5. Now I'm back into regular integers. I know how to deal with this. I get x times 2. I just divide by 2. That kills that. And I get that x is equal to 5/2. When? Well, x is equal to 5/2 when y is equal to 0, right? That's what we were trying to find the whole time. 5/2 must be where it goes through, right there. And now we are done with that one. We have both points labeled. We have our axes labeled. We are good to go. Now, to determine which of these are functions, right, after graphing them, it becomes pretty easy to see. So like in the first case, we had y equals negative 2x, and so it went through like this. And now we could ask, like, well, think about the vertical line test. Like, does this pass the vertical line test? Yeah, sure. I mean, it only, no matter where, it only touches at one point. Another way of saying that is for any one input, we get one and only one output. There aren't any lines that bend back over themselves to give you two outputs, right? So it turns out then that almost every line is a function. right? Here's one with a negative slope, and we could just see that, yeah, every one input gives you only one output. There's my one input, and it gives you only one output, and so that's perfectly good, right? Ditto with a line with a positive slope, right? Your slope is positive, okay. It gives, for every one input x, it gives you only one output. Sure thing. Nice, good to go. What about a horizontal line? This is where the English that we're using gets a little strange, because when you hear this, it's like, yeah, every one input gives you only one output. But, oh wait, but everything gives you that output, right? Oh, hold up. Let's just think about this. One input, x, gives you that one output. Okay, so that's good. Here's a different x. Let's call it x2. Plug it in. It may give you the same y value that the first one did, but it's only one of them, right? This line never comes back over itself to give you two outputs for one input. So a horizontal line is perfectly good. It's a function. It is, by definition, one input goes to one output and you're done. The only problem then comes with a vertical line, right? So when we have a vertical line, let's do this real quick. We'll do the one that we had earlier where x equals -3. That's part E right there. There's -3, and the line was a vertical line. Now here's a problem, because we have one input, namely -3, and how many outputs do you get? Well, all of them. Every real number, right? You get 1, you get 2, you get 3, you get pi, you get 7, you get a billion, you get -1, negative, you get all of them. Every real number is an output. So this is certainly not a function, right? One input gives you multiple outputs. So this is not a function. So the final answer there is this is not a function, because one input gives you multiple outputs. The rest of them, and you could argue just by the graph, right? We're not looking to do any hard analysis on this or anything, but just by looking at the graphs, we could see, yeah, every other kind that we did, right? Just like I said a minute ago, this one is a function, that one, even though it's horizontal, perfectly good function. All of the other ones are perfectly good functions. The only one that's not a function is that guy right there. I realized that when I recorded this yesterday, I did not include the last part of part G, which is what's the domain and range for each one of these functions. Now, as we talk about in lecture 1, it's really, if you graph the function, it's real easy to see what the domain and range are, with lines especially, because, okay, so this one right here is the line y equals 2x. We're going to think about it as f of x equals -2x. And of course with domain, we think these are all of the allowable inputs, right? And with 2x, all inputs are allowable, right? We could say that you could plug in 0. You always want to check 0 when you're checking domain. It's a good place to start. Say, can I plug in 0? Yeah. Can I plug in any number bigger than 0? Yes. Can I plug in any number less than 0? Yeah, you're just multiplying a number by that. You could do that with any real number. So there's no problem with that. In fact, I'm going to go ahead and say the domain of f is, we could either think about it as the interval from -infinity to infinity, which is nice because that kind of goes along with our picture here. Okay, we could also call this the set of real numbers, all real numbers. That's perfectly fine too. Either one of those you want to use is cool. And now, when we're thinking about the picture here, the picture that we've drawn, we could just say, okay, the domain are all of the input values, x, and we could say, is there an output for every input value? Like, are there any holes in this anywhere where it's not defined or anything like that? Do we end up with anything crazy? Well, no, this is a line. This is about as well behaved a function as you could possibly get. We know this goes on forever in that direction. It goes on forever in that direction. And so we could say, yeah, for any given input, right, we could plug it into here and find some output. So a couple ways of looking at domain for that one. And now for the range, what we do, remember our new definition of range, it's the output values we get when we plug in the entire domain. So we're going to take the whole domain, right, all real numbers, and we're going to see what outputs do we get. And here, another way of thinking about that is what values get hit when you plug in the domain. So here's just a couple. When I plug in this number here, that number is my output. That number gets hit. Plug in this one, and my output is that number right there. And we could see, yeah, since we're taking all of this, right, we're taking the entire real number line, we are going to get every real number out, right? Take over here, plug that in. Every real number is going to be an output. Another way to kind of just visually or pictorially look at this is simply we just draw lines, just kind of like what I've done here. But we could just imagine, there's another way of thinking about it, is if you were to take a flashlight, right, and you were to shine a light onto this function, what shadow would it create? Well, all of these points here would get projected onto the y-axis. Ditto over here, right? Have our flashlight, and we shine our flashlight. What would we see? Well, that would cast a shadow here and here and here. This entire thing would get projected onto this line. And there's no value in the output that doesn't get hit, right? 0 is hit. Clearly, when we plug in a 0, we get out a 0. All the positive values are going to get hit by this function. All of the negative values are going to get hit. And so, finally, we could say then, in this case, the range of f is all real numbers. Just as an aside as well, like, this guy matches up really well with this picture here, right? If we're thinking about this as the real number line, we have negative infinity way down there. We have positive infinity right way down there. So this interval matches up with this right here. We're saying it's the entire thing. This guy, we're writing him horizontally, but we know what that stands for, right? We have a negative infinity down here, and we have a positive infinity up here. And so what we're saying there is you take that interval and kind of, that's the interval. Those are the set of outputs you get when you plug in the entire domain. To really beat a dead horse, let's return to what we did earlier today in lecture 2. We had this function, which I didn't actually give it a formula in class. I just said, well, we're just going to call this thing f of x. It turns out what I had done was I drew the parabola f of x equals x squared plus 1. And we said earlier in class, and we're not really going to think about this right now, but in class we said that, well, this goes all the way in that direction forever and all the way in that direction forever. Therefore, all real numbers have outputs, right? And so we could say then, and we did say, that the domain of this function is all real numbers. Everything from negative infinity up to infinity. And then we talked about the range, and we said, you know, it's then what you get when you plug in all these real numbers, and we did this where we went up to here and then we went over to there. Now just what I want to talk about is, if you understand that that's what you're doing, that you're plugging in all these values, let's just skip that first step where we're plugging this part in and seeing where the arrow goes, and we could return to our idea of shining a flashlight. If I shined a flashlight onto this, then all of these points would cast a shadow on this y-axis here. Same thing over here, right? We got to go from both sides because you kind of see what's going on, right? I'm talking about casting a shadow. What's really happening is we're talking about at this point comes from an input here, and then its output is that number. But we're going to skip that step right now and just say, well, if I shined a light, what numbers would get hit? And we end up with the same picture, right? Also shining a light from this side, the shadow's getting hit here. We end up with this same picture, and we could see, okay, well then what's going to get hit are all the numbers from 1. 1 is one of them, right? Because when we plug in a 0 into this function, plug in a 0, we get out a 1. Get out a 1. So 1 is one of the numbers that does get hit. We're going to include that guy. And we see that this is going to go all the way up to infinity. It's never going to stop, right? Because you could just plug in bigger and bigger numbers, right? As you plug in bigger real numbers, you'll get bigger output numbers. And so thinking about this then as another interval, we could say, oh, that's the interval from 1, including 1, all the way up to infinity. And that indeed is how we're going to write the range. So we could say the range of f is equal to closed interval from +1 all the way up to infinity. That's the picture that goes along with it. This is what I really like about this, is that interval then is just that interval right there. And so again, when you're trying to write a set in interval notation, it's really nice to have that picture of the line that you're dealing with. And that's all we're doing with the range as well. We're just seeing what set, in other words, what part of the real number line is going to get hit by the input values when we put them in. Moving on to find the domain and range of each of these functions. Let's see, we're just going to graph them and make it that. Makes it so much easier to wrap our heads around it. Y equals 5 is the horizontal line, goes through here at 5. Its domain is, well, all real numbers, right? We can see that you pick any real number and it tells you, yes, there is an output and its value is, and it tells you what its value is, right? We choose this real number. So again, doing it systematically, like I said, can you plug in 0? Well, yeah, again, this thing doesn't even have x in it, so we have no problems plugging in 0. You see, and that's where it gets kind of weird, and it's nice to have a picture. When you're trying to think about it just abstractly like this, you're like, well, I don't know, can I plug in a 0? It doesn't show up over here. But if you have it like this, it's like, yeah, okay, that means that when I plug in 0, I get out of 5. When I plug in a 1, I get out of 5. When I plug in a 10, I get, yeah, and so we could plug in 0. We could plug in any positive number. We could plug in any negative number, and we're good to go. So then the domain of f is going to be all real numbers. Okay, what about the range? Well, we're looking at all the outputs. We're looking at everything that the output hits. If I were to shine a flashlight right here, what would get projected onto the y-axis? And we could see that the only value that is an output is that number right there. It's the only thing. It doesn't matter where you come from. If you come from here, the rule says, okay, take it and go to 5. The rule says if you come from -100, take it and go to 5, right? It's always 5 forever and for always. And so when we plug in the entire domain, the set of outputs that we get is simply the number 5. And we'll put that in brackets like this, or curly braces, whatever we want to call it. And we get that the range of f is the number 5. Okay, moving on. We have, when f of x is 2x plus 3. No problems here. I could plug in 0 and multiply it by 2 and add 3. No problem. I could plug in any positive number. I could plug in any negative number. Every single real number is good. And so the domain of f, again, is all real numbers. Okay, and let's see. I'm going to use the picture to help inform us. I know that that is a positive slope and it goes through at 3. So it looks like that. And now I could see, yeah, it's take the guesswork out of it. Let's just project this line onto its outputs, and we can see that, yeah, every single output is given. It's going to be the case with most lines. Almost all lines are going to be like this. There's only a couple cases where that's not going to be the case. I wonder if you could figure out which ones they are. But again, the domain is all real numbers. Why? Because we could plug in any real number and get a legitimate output. It is allowable to plug in any real number into that formula. Conversely, give me any output. Choose your favorite real number output. Mine at the moment is 17. And we could say, is that an output of this right there? Well, let's see. 17 equals 2x plus 3. And indeed, yeah, we could solve this, right? And we would get whatever 17 minus 3 is. I can't do that in my head. I think that's 14, 15, 16, 17. Yeah, that works. Okay, 2x divided by 2. And we get 7 equals x. And yeah, so if 17 is your output, it must have come from an input. We could do that with any real number. That is, all real numbers are indeed outputs of that guy. But again, I'm going way too far into this. We could just look at the picture and see, yeah, those are all the outputs that get hit. That goes up forever. That goes up down forever. There's no holes in this or anything, so every real number will be an output. So domain is all real numbers. Range is all real numbers. The next one, f of x equals, we can rewrite that as y equals negative x plus 1. So let's do that. F of x equals negative x plus 1. I just went ahead, I think that's earlier in the video, but I just solved for y, right? And we could see, okay, this guy goes through at 1, has a negative slope. And so, again, domain, no problems. We could plug in any real number. The range, I could tell from the picture, all real numbers get hit when I project this line onto there. Every single real number is going to get hit, so we will end up with all real numbers. Okay, now, here is where things get a little bit interesting. We can't even write this as f of x, can we? Because it's just x. It's just the relationship x equals 3. Or sorry, minus 3. And so we end up with the vertical line here at minus 3. Now we've already said it's not a function. It's certainly not a function. We could still give an idea of what a domain and range are, right? It still has a domain. It has, you can think about it as inputs when we think about this. It has outputs. Now it's not a function, it's something different, but it's still, whatever it is, has a domain and range. And so I'm going to say then the domain of this guy, and notice I'm not calling it, I'm not putting a function in there, it's a little tricky, right? So, but whatever, we're just telling you that the domain, in other words, the input, the only input, because we're thinking about this axis as my input axis, the only input that we have is negative 3. So that's going to be the singleton, negative 3. That's called a singleton set, by the way, if I haven't said that already. A set with one thing in it is called a singleton set. Doesn't matter. Now, let's see what my outputs would be. Well, pretty obvious. We're shining a flashlight onto here. then it casts a shadow over the entire real line. 0 gets hit, 1 gets hit, 2 gets hit, they all get hit. So we're going to say the range of this thing, which isn't a function, but whatever, the range would be all real numbers. Now if you happen to say something like, this is not a function, this is not a function of x, and just stop there, I'd respect that. I'd be like, yeah, you're right, it's not, and we haven't defined what the domain and range are of anything besides functions, right? So this isn't a function, and so it does have a domain and range if we want to define domain and range for things that aren't functions, but we haven't. So if you wanted to just say, no, I think you're trying to trick me, there is no domain and range, that's fine too. That's cool. But we could think about it this way. Either way, I'm not going to be particular about that. Finally, the last one. We have this guy, which we can turn into, real quick, y equals 2/3 x plus 5/3. And so we have f of x equals 2/3 x plus 5/3. What does he look like? Now, and of course we could do this where we're thinking allowable inputs, and I look at the formula and I say there's no problem with that. You could multiply any real number by 2/3. Whatever you get out of that, you could add 5/3 and you get a perfectly good thing. There's no rules being broken, we're good to go. And we could say then the domain should be all real numbers. We could also look at it like this once we graph it and say, okay, positive slope goes through here at 5/3. And so, yeah, it's any input has a corresponding output. This rule, I'm not thinking about this, this rule tells me, it's like a map that tells me if you're here, if your input is here, then your output is there. It's a relationship between x and y. And I could see that since it's understood that this goes on forever, then there's no problems. Every single real number will have a corresponding output. And so, again, the domain of f, is all real numbers from negative infinity up to infinity. And the range, well, let's think about it. Look, this gets mapped there, right? These all get mapped here. Every single number, if I took lights and shined them in, they would, every single point would cast a shadow on the y-axis, and there's not one point on the y-axis that wouldn't be hit by a point. And so again, that's all real numbers from negative infinity to infinity. So the only real thing, the thing to notice is that almost all lines have a domain of all real numbers, and their range is all real numbers. There are just really two limiting cases where that's not the case. That is in the case of a horizontal line. And for a horizontal line, right, the domain is all real numbers, but the range, in other words, the output, is one single number, a singleton set. In the case of a horizontal line, in the case of a vertical line, then the domain is one single number, but the range is all real numbers. Problem 4, graph the functions and label any intersections of axes and stuff like that. So, first off, we have f of x equals x squared. Now, this is called a parabola. Now, let's go over why it's shaped the way that it is. So, we're going to have our x-axis here, our output axis. Now, for part A, you could do this any way you want, really. I'm not going to be a stickler about this. We could call this the y-axis. We could call it the f-axis, thinking about like, well, there's your relationship between x and f. But if you call it y, it doesn't really matter. Certain cases you'll want to do that, but I'll never demand that you do that. But yeah, okay. So let's think about this now. Let's think about some different x inputs that we have. We're gonna do, how about 0? what f says to do, it says take your input value and square it. That is, multiply it by itself, whatever that input value happens to be. So when I plug in a 0, I get that f of 0 is 0 squared, or 0 times 0, which, like, yeah, I bet you could guess that's a 0. F of 1 is 1 squared, or 1 times 1, which is 1. F of 2 is 2 squared, and now we get 2 times 2 is 4. Okay, interesting. Now what about if we went on the other side? Oh, let's just plot these real quick. So when I plug in a 0, I get out a 0. I plug in a 1, and I get out a 1. I plug in a 2, and I get out a 4. Okay, what about when it's negative? Well, plug in a, let's do it like this. Plug in a negative 1. I get negative 1 squared. Negative 1 times negative 1, and negative times a negative is a positive. We get positive 1. When I plug in negative 2, I get negative 2 squared. Negative 2 times negative 2. Negative times a negative is a positive, so we get positive 4. So let's just plot these. At negative 1, it goes up to 1. Negative 2, it goes up to 4. Now you can just kind of imagine that if we were to connect all of the other points, in fact, let's just do a couple more. Let's go 1/2. 1/2 is halfway between 0 and 1. Really, it really is. So what happens when I do f of 1/2? Well, it's just by definition, right? We take whatever's in there and we square it. So 1/2 times a half, right? Half times itself. It's the same thing as 1 times 1 in the numerator and 2 times 2 in the denominator. So that's just a 1 over a 4. So the reason I wanted to show this here is that this is not like a straight line. This doesn't come straight down like this. When you plug in a 1/2, you don't get out a 1/2. You get something smaller, which is a quarter right there. And in fact, the smaller that number gets, when you square it, it gets even smaller, right? So like when we're at 1/10 and you square 1/10, you get 1 over 10 times 1 over 10. 1 times 1 over 10 times 10, that's 1 over 100. And so now we're way down there, right? And so what this does is it kind of scoops up this way. It starts really low, moves, and then starts moving up faster like that, right? You can think about it as the slope at the point, foreshadowing things to come. That it starts off flat like that, and then as you move, it starts going faster and faster up that way. Right? I'm not going to worry about that too much, but just to get the general idea, that's why it is. It's not just a straight line that goes out like that. It starts low and starts coming up. Now, okay. What about when it's bigger? We notice what's happening, right? So in the same way that when you plug in smaller and smaller numbers less than negative 1, they get really small. Now when you start plugging in bigger numbers, they get even bigger, right? So like if this was my original line, just the line y equals x, right? It was going below the line because when you square a number less than 1, it gets really small. But now when you square a number bigger than 1, it gets much bigger, right? And so now you're out here. It does something like this, right? And now you move, so we moved over a quarter and we only went up, we moved over by a half and we only went up a quarter. We move over by 1 and we go up 1. But now, move over by 1 and we end up going up by 4. If you're kind of thinking about slopes, right? Like if we're thinking about the rise over the run. So for this part right here, the run was 1, and the rise was, I guess, 3, right? There's 3 between 4 and 1. Now when I go from 2 to 3, let's see, when I plug in a 3, f of 3 is 3 squared, which is 9. So now it's even further up there, right? Plug in a 3, we're up here at 9. And now, okay, so it started off, you run 1, you go up 1. Now you run 1, you go up 3. Now you run 1 and you go up whatever 4 minus 9 is. I guess that's 5, right? You go up by 5. So it's like, it's as though your slope is constantly getting steeper and steeper and steeper, right? So that's what's happening. That's why we end up with this cup shape. It's nice, and I haven't drawn it nice and smooth, but it's actually nice and smooth, and that's what's going on right there. And we could kind of see, right, like if you plug in a negative number, right, if you're out at 2 and you plug in a negative 2, you get the same output, right? When you're at 1, you get 1 as an output, but when you go to negative 1, you also get 1 as an output. Every output that's over here is exactly mirrored on the other side, and we get this nice, it's called a reflection, or we could call it a reflection. It's like a reflection over the y-axis. And so that's the general shape of a parabola. And indeed, that's the answer to part A, but I don't expect it to look like this. This is really, really messy. For your answer, I would say, if you did this, X, you call it Y, you call it F, I don't care at this point. It goes through right here, and then goes up like this, and goes up like this, and you're done. That's it, right? That is the graph of f of x equals x squared. Part B, g of z is equal to negative z squared. Don't let these letters confuse you. This is all we're doing. If you ever doubt what's going on, this always tells you what the input is, right? We always put our inputs as going into the functions like that. So then by definition, this has to be the z-axis. I'm going to label that as z. The output, you could call it y, you could call it g. I don't really care at this point. We're going to call it g. If you didn't, that's fine. I'm not worried about that. But it is pretty important that we call this the z-axis. So, okay. The only real difference here between this one and the last one is that negative sign right there. So let's first think about f of x, our original f of x. F of x was x squared, but let's just, now that we're on the z-axis, let's just say, well then f of z must be z squared. Same exact picture, nothing's different, right? When I plug in a 0, I get out a 0. Plug in a 1, get out a 1. Plug in a 2, you get out a 4, and it does something like this. Same thing on the other side. Plug in a negative 1, you get out a 1. Plug in a negative 2, you get out a 4, positive 4, right? And so we end up with that kind of picture. Now, the only difference then is that this guy says, okay, take all those values. You've taken each one of those values, now make it negative, right? In other words, what I'm saying here is that g of z is the same thing as you took all of the output values of your original f of z, and then you just said, well, just make it negative, right? So what would that look like? Well, you plug in a 0, right? You get out a 0. Negative 0 is still 0, so we're still here at 0. Now let's try with 1. It used to be you plug in a 1 and you get out a 1, right? With the original, with the f of z, right? Well, now we're just saying, okay, plug in a 1, you get a 1 squared is 1. Now make it negative. Oh, okay, well, I would get a positive 1, but now it's just going to come down here to negative 1. Okay, it used to be that when I plug in a 2, I get out a positive 4. Why? Because z squared, plug that in, 2, right, plug in a 2, you get 2 squared is positive 4. Now we're just saying take that and make it negative, right? You can kind of see that here, right? Plug in a positive 2. 2 squared is 4. Then make it negative. So it comes down here to minus 4. And what we're ending up with, if you notice it, it's like another kind of reflection, right? It's like you've taken this thing and now you're just taking all of these points and then making them negative. And guess what? This point's going to get mapped down to here. This point's going to get mapped down to there. Every positive output value that we had from the f, it's like we take those positive output values and now we're just making them negative. We're saying just whatever you got originally, just make it negative. Ditto over here. Take those, make them negative. And let's just check. Let's just check one more time to be sure here. Plug in a 2. If I plug in a 2 to f, negative 2. That should be a negative 2. Okay, so I take my original f, plug in a negative 2. Okay, that gives me negative 2 squared. Negative 2 times negative 2 is positive 4, and so yeah, indeed, this comes out to be, it's not drawn very well, but you get the idea, right? It goes up to positive 4. Now what happens, in fact, I should just go ahead and put him out more. Say, right there, there's negative 2. That's where negative 2 lives, okay? Plugged in the negative 2, positive 4 popped out. Now what about in g? G of negative 2 says negative 2 squared. Oh, okay. Negative 2 squared. So we take negative 2 squared is the same thing as 4. Oh yeah, exactly what we got before. And then at the very end, I just said, well, now just make it negative. So we took the point that was up here and brought him down to here. And so, see, this is another kind of reflection. We're reflecting now over the z-axis, or the input axis. Right? Okay, so that's your picture right there. The only thing to label is 0. And again, I'm not looking for all of these points that I put up here. If you did this, if you just did this and this, then we call that Z, we're going to call that G, and then just say, okay, it's like the original one, but now we've just taken all of them and flipped them down, and so we get something that looks like this, downward facing cup, or downward opening cup, goes through at 0. We've labeled the only place that it intersects anything, so we are good to go. H of A equals A squared minus 4. Now, you can tell I'm playing with the input variables, right? Like, when I see this, I think of like, well, it's like H of X equals X squared, right? Like, this is actually what goes through my mind. Just because I'm so used to dealing with X's as inputs, you know, like, but that's really what I'm seeing there. Then I think, well, hold up. this is just like that original function we had there, which I guess last time we did it in green, so let's go ahead and do it again. We could say f of x is x squared. So that's like I'm taking f of x, that original function that we graphed, the original just regular parabola, and then after drawing that, we're just going to take all the output values and subtract off 4. What do I mean the output values? Remember, this thing represents the output value, which I said we could call h or we could call y or whatever. You know, it's the horizontal values. So when you plug something into here, it's the same thing as evaluating this guy first. And then you go and say, well, now just minus 4 off of the height. Let's see that in action. What's that going to look like? Well, the original guy, we know what he looks like. We don't need to use our brains anymore for this. We know that x squared looks like this. So that guy is x squared. And yes, I'm using x's right now and not a's. So now this says to do, what h says to do, is take each of those values and then subtract 4. Right? So when I go through here at 0, 0, what h says to do is take that value and bring it down 4 units. So we're taking this value, shifting them down 4 units, and it goes through here. Now what I'm going to do, I'm going to go through this talking about this as a translation of our original function. Then we're going to go back and kind of prove that to ourselves. We'll convince ourselves that that's true in just a second. So, okay, the original value, the x squared value here at 0 would give me 0, but then I'm going to subtract 4, so it comes down. Okay, now it used to be I'd plug in a 1 and get out a 1, but now we got to subtract that down, right? So think about that. H of 1 would give me 1 squared minus 4. What did I just say? That's the same output as that guy, which would be up here at positive 1. And then we subtract off 4. We're bringing him down 4 units. So I guess down 4 units would bring him to minus 3. Okay. Used to be we'd plug in a 2 and we'd get out a 4 into that original function. It's 2 squared is 4. But now, when I plug in a 2, I get 2 squared minus 4. And, oh, hey, that's nice. I get 4 minus 4, which comes down to 0. And let's just see, like, is that what happened here? Yeah, it's the same thing as before. It's like taking the original x squared function and then just dropping him down 4 units to hit right here. And so you'll notice I don't want you to get all of these crazy points and draw everything the right way. All we really need to do here is say, well, wait a second. This, I've already graphed that. I know what that guy looks like. Now, after graphing that, then I'm going to bring him down 4 units. So this picture right here, this green picture that I drew, we'll just slide it down 4 units. And we'll do something like that. And there you go. But, so that's basically where we're going to start off with this. Problem's going to be, we're going to need to get all the intersections. And we're going to do that special way. And we're going to go back to thinking about this as A. Okay, so now we are going to graph this function. And I can see that the inputs are A's. Okay, the outputs are Y's or H's. I'm not too particular about that. But now, just like we said, right, I recognize this as, oh, that's just like that is just like x squared. So if that were an x, right, we would have this cup that goes through right here. Now we're just taking that cup and dropping him down 4 units. Okay, so we don't need to be particular or do any kind of measurement here. I know that the cup is going to start here and then go up like that and go up like that. That easy. Okay, not measuring anything. Now, what we need to do is find these 2 points. We know that one's -4. And if we're not certain about that, how could we find the y-intercept? Well, the y-intercept happens, right, when the horizontal axis equals 0. So in this case, we're going to say h of 0. When the input is 0, then the output is, oh, what do you know? 0 minus 4, it's equal to -4. Just like we drew. And we only used just the idea of translating a graph that we were already familiar with. So, that checks out. That's a good one. Now, the question is, what about these guys? Well, that's when the output axis, these points occur when the output is 0, right? When, yeah, we could think about that as the h-axis, or the output to this function is equal to 0. So that's how I'm going to think about it. I'm going to say when 0 is the output of a squared minus 4, and then what value is a? And already I kind of know from the picture, well, I'd better get 2 answers here, right? Because, well, look at that, right? It looks like there should be 2 things. And yeah, that's what we're going to find. I'm going to start by, I'm trying to get a by itself. So a gets squared, then he gets 4 subtracted from him. So I'm going to say, well then, to undo subtract 4, I'm going to add 4 to both sides. I get 4 equals a squared. Now, we're going to take the square root, whatever that means. So I take the square root of a squared, and it gives me a. When I take the square root of this, it's actually kind of subtle. When you take the square root of a number, you get 2 answers. You get a positive and a negative answer. Why? We'll get to there in just a second. What we're asking here is, what number, right? That the square root asks, it says, the square root of something says, like, okay, there is, that this is a specific number that when you square it, there's a specific number, so that when you square it, it gives you whatever is in there. In fact, it's the inverse operation of squaring, right? We're just saying, hey, you took a number, multiplied it by itself, right? So in other words, you took a number, multiplied it by itself, and you got whatever is in there. So we said, okay, there's a 4 in there. You took a number, multiplied it by itself, and got 4. Well, I know what that is, right? That's 2, right? Of course, 2. 2 works. But that's not all that works. -2 also works, doesn't it? Right? You could say, well, it's also true, like, yes, 2 works here, right? But it's also true that -2 works there, right? And that's what we mean by this plus minus thing, right? Is that this means, like, you actually get 2 answers here. A is equal to 2, and A is also equal to -2. And that's what we expect from our picture here, right? I'm going to go ahead and label these points and say, like, we expected that from the very beginning. It's like, I just set this equal to 0, and we could see that there are 2 places where that's true. Now, let's just double check that this works in our original function. We claim that when A is equal to -2, right, when the input A is equal to -2, then the output should be 0. So let's see, we get -2 squared minus 4. Negative 2 times negative 2. Well, a negative times negative is a positive. 2 times 2 is 4. 4 minus 4 does equal 0. So that point checks. What about h of positive 2? Well, it says we do this. 2 goes in, 2 goes in here. 2 times 2 is 4. Minus 4 does in fact equal 0. Okay, so we're good to go. That is what I'm looking for right there. That's the picture. I don't care if like this is about the same length as that. I don't care. This is a qualitatively accurate picture. D, y equals 1/2 x minus 1. This is a lot like from the last problem, right? Just graphing a line. I just wanted to kind of show this because it's like, well, we can think of a line as a function, right? Y of x. And in this case, we have y of x is equal to positive 1/2 times x minus 1. So I'm thinking, aha, yeah, this is a line, right? It's in this form, mx plus b. Right, and so the slope here is 1/2. The y-intercept must be negative 1. And so when I go to draw this guy, I'm going to think, all right, the input values are x's, so I'll label this as x. Outputs are y's. Now, okay, plug in a 0, you get out a negative 1. So there it is, negative 1. It's a positive slope, so I'm going to draw it like this. Positive slope. We're not quite done. We have one more place right here that it goes through. Now we just need to find that. So I'm going to say, well, there the output value is 0. Looking for an input value. Sometimes it's like, wait, which one am I setting equal to 0? And it's like, well, what are you looking for? I'm looking for an x value. So x, I can't plug in 0 for x and get x. It'll just disappear, right? So it's like, oh, right. The 0 is the y value. So I'm going to say, in other words, the output value. When the output value is 0, what's the input value? That's what I just said, right? Looking for some value x that when we plug it in, we do this, and then out pops a 0. So, trying to get x by himself. So let's, how about add 1 to both sides? Okay, and drop this down here. We'll say 1 equals 1/2 x. Fractions, I hate fractions. Let's clear the fractions. I could kill that 2 by multiplying by 2. Okay. I get 2 times 1 is 2, and those canceled. That's why I did it that way. X times 1 is just an x, and so x equals 2 right here. And there's your picture. That's what I'm looking for. I don't care that that slope doesn't really look like a 1/2. It's qualitatively accurate, and so we're done. Part E, z of t is 1 minus z. I'm sorry, yeah, z of t is 1 minus t squared. So I gave a hint, right, and said, think about this right here as that guy that we already did, right? So let's just kind of keep that, get that fresh in our heads. What did we do there? We said, well, this is like that, but it's just been reflected down. It's the downward facing cup, right? So negative z squared, or in this case it would be negative t squared, looks like that. In fact, I'm going to go ahead and say that this right here, that function, is negative, let's do it in t, negative t squared. That's what it looks like when we are on the t-axis. Double check if you don't believe me, right? Plug in a 0, you get out a 0. Plug in a 1, you get 1 squared, but then you make it negative, so you get negative 1 squared. Right? Yeah, that looks good. Plug in a 2, you get 2 squared is 4, but then you make it negative, you're down here at negative 4. Ditto for all the negative numbers. We're good to go. Now what have we done? Well, what I was saying in here is you could think about that as saying, well, first you take t squared, then you make it negative, then you add 1. Right? And it doesn't matter if you add 1 before or after, you know, or, well, if you, the way this is written, it doesn't matter if you write it as 1 minus t squared or t squared minus 1, you end up with the exact same number. And so then what does this do? Well, this is like saying we took this guy and then took all the output values and added 1, right? To be explicit, it's like saying take this green object, which is negative t squared. You have all those outputs right there. And then you're going to add 1 to it. And that will be your new output, which we're calling z. I guess we'll go ahead and label this as z. Okay, well then, if we were at 0, 0, right there, then adding 1 to the z values is going to bring him up to 1, right there. And we plugged in, well, we could figure all that stuff out. In fact, I don't want to think too hard about this. I know that I'm just taking this entire shape and pushing him up like that. So it's just going to look like this. Okay. Now that's pretty good. The only problem is now we have these guys to worry about. And so let's find out where that happens. Okay. Get rid of this. And say, all right, we are dealing with z of t. In fact, it's right here. I'll write it the way that we had it, or the way that it was written. Z of t is 1 minus t squared. And let's just check, make sure that our shifting actually worked. When I plug in a 0 for t, I get 1 minus 0 is 1. Yeah, so when the input is 0, the output is 1. That looks good. Now, we want to find out where it goes through the x-axis, or the t-axis, the input axis. So we were trying to find inputs. We want to find inputs for when the output is equal to 0. So when the output is equal to 0, we get that right there. All right, we're trying to find these input values of t, so that when I plug them in, the output value, the height, is 0. Okay. A few different ways of doing this. I don't like working with negatives, so how about we'll just add t squared to both sides, and we get t squared is equal to 1. So some number multiplied by itself equals 1. I think that's 1, right? T should be 1. Oh, but t should, and we know we should get 2 answers here, right? And so we get both negative 1 and 1, right? We could do that deliberately by taking square root of both sides. You take the square root of a number, you actually get a plus and a minus, and so you get plus minus, square root of 1 is 1, and there you go. 1 and negative 1. Now let's just check, and it's pretty easy to see. I'm not even going to write anything down. When I plug in a 1 into here, I get 1 minus 1 squared is 1. 1 minus 1 is 0. And so when the input is 1, the output is 0, which is what we see right there. When the input is negative 1, plug in a negative 1, 1 minus, well, negative 1 squared is a positive 1. 1 minus 1 is 0, and that is what we see. The height right there is 0. So that is a perfect picture right there. And that's what I'm looking for. Okay, part F. Q of P is equal to negative 3 halves P plus 1. This is just a line. There's no difference, right, in between this and anything else other than, instead of calling this X, we're calling it P. The output, instead of, say, being Y or whatever, we're calling it Q. Okay, no problem there. We're going to go ahead and get this started. Input values are P, that means we're on the P axis. Output values are Q. We could call it Q, we call it Y. Don't really care. Now, just thinking, well, wait a second. Yeah, why is that a line again? Well, Y equals mx plus b. It's what we usually think about for a line. But now our Y's are Q's. Okay, and our X's are P's. Okay, well, that's what we have here. We have the slope, right? Some number, some constant number, times the input variable. So that slope is negative 3 halves. And then plus or minus a constant number. And so that's what we got right there. The Y-intercept is 1 because that is 1. We could think about that a couple different ways. I like thinking about it as a function, right? I want to know how high up to go right here. The p-value is 0 right here. Plug in a 0, all that goes to 0. My output is just a 1. It's a negative slope, right? Slope is negative, so I know it has to go down like that. And so I'm going to go ahead and do that right there. Now, okay. One more place to find. It's wherever it goes through right here. And we're going to say, well, the height is 0. That means the output is 0. We want to know what input, what p-value, gives me 0 as an output. So we're saying we're trying to find out, given this right here, what p-value gives me 0 as an output. I could subtract 1, or I could add that guy to both sides. I think that's what I'm going to do. Plus 3 halves p at both sides. And we get 3 halves p equals 1. I hate fractions. Let's kill that fraction. How about multiply both sides by 2? Okay, that cancels that. I'm left with 3p equals 1 times 2 is just 2. Now, p gets multiplied by 3, so to undo multiply, we divide. P equals 2/3. And so the input value is 2/3. Rather, when the input value is 2/3, my output value should be 0. And yeah, if you want to plug that in and check it, you can see that that's exactly what's going to happen. Just kind of double checking, like I didn't end up with a negative and then draw it like that and go, well, wait a minute, whoa, that's not a negative number. That should be a positive number, right? Like everything checks out. A positive 1 should be up there. A positive 2/3 should be on this side. And so that's what I'm looking for. Problem 5. I define 3 different functions and tell you to compute these values. Then in part H, I ask you to give the domain and range for D through G. Then we want to find a formula for the inverse function of each. So, all right. First thing to note, and this is kind of a technical detail here, is that when I write the square root of x, I mean the positive square root of x. Now, if we had an equation like this, squared equals, oh, I don't know, how about 25? And then I took a square root. What we're going to say, at least in our class, the way we're going to do it is that when you take a square root of something, then you get two answers. You get a positive and a negative answer. And so we say when you take the square root of a number, you get a plus and a minus. Taking a square root undoes square. It's the inverse operation. And then what you get are two answers, plus and minus the square root of 25, which is plus and minus 5, because 5 is the square root of 5. That is, x is it's either minus 5 or 5. And we could see that that's true. Going back to our original equation here, we could see that both of these work. If I plug in a negative 5 and I square it, I get negative 5 times negative 5, which does equal 25. When I plug in a 5 and I square it, I get 5 times 5, which is 25. And so that's cool. So in the context of solving an equation and taking a square root, then we have to consider both the positive and the negative outputs, or both the positive and the negative answers, because we can see, well, both of them work. Both of them solve this equation. Now, when I just write a function like this, I mean the positive square root. If there's not a negative sign in front of it, I'm talking about the positive square root. So it's understood that we're not talking about this guy in this case, right? So just so you know, from here on out, that's how we're going to deal with that. Okay, so let's just plug along and see. These first ones are really straightforward, right? I'm literally just saying, hey, plug in a number and calculate it. So f of minus 2, well, by definition of f, everywhere that I see an x, I put it right there and then just add 1. And so whatever's in there goes right here. And so that goes to there. And I get minus 2 plus 1 is just minus 1. Okay, cool. What about g of 4? Again, by definition of g says take whatever's in there and then take the square root of it. So the same way there's an x there and an x there, if there's a 4 there, there's a 4 there. And so this positive square root of 4 is 2. In other words, 2 times 2 equals 4. So the inverse of that would be 4. You're taking the positive part. Okay, h of 0. Let's see, let's plug it in. H of 0, well, h says take 1 over whatever the input is, so I go 1 over, that's undefined. So the answer I'm looking for this one is h of 0 is undefined. Okay, we've talked about that. We know why it's undefined, right? Division by 0 doesn't make sense. So, okay. Now, f of g of x. So now I'm asking for a formula, right? And so what I like to do, let's imagine that I have some really complicated formula here. I don't know, maybe it's 2 times x plus 1/2 quantity squared. Let's not make it plus 1/2. Let's go. Okay, so now if I gave this formula to you and I said, now evaluate where x equals, how about 1, right? What would you do? You'd say, well, first thing I need to do is take 1 and put it in here, right? So in other words, what you're doing is you're looking at the innermost thing, right? You're finding x, and then we're going to work our way out and see what happens to x. So we would first plug in a 1, right? In fact, let's make this a little bit more complicated. Let's say that we had 3x, like that, right? We would first plug in a 1. We'd say, okay, plug in the 1. Okay, now 3 times 1 is 3. Okay, plus 1 squared, 2, and the root. Then we would have to say, okay, 3 plus 1 is 4. Okay, so 4. And you can see what's happening, right? I'm kind of working my way out from that original x that was right there. And, okay, what would we do? Well, then 4 squared is 16. Okay, so then 2 times 16, and then 2 times 16 is, I guess, 32. We take the square root of 32, and so on and so forth, right? The point is that we're starting from the innermost thing and working our way out. I'm going to suggest that that's probably the best way of dealing with these guys right here. Right, we have a bunch of stuff on the outside. In the end, what we're going to do is mess with f. But if I were to give you, if I were to say, what is f of g of 4, you would say, well, hold up. 4 is the thing you're plugging in, and so then you would go into g and plug that. Oh, we already did that. You'd get out a 2. Okay, so that would be the same thing as, we know that g of 4, when I plug in g of 4, that means exactly the same thing as that right there. So this symbol would then be, we could then replace it with this symbol right there. We could say, okay, that's what that means. Then we could go and say, okay, now we know this. Now I'll just plug in f of 2. Well, what's the definition of f? Well, f says to take whatever goes in plus 1, so we would just then say, okay, 2 plus 1 equals 3. Okay, but notice how we did this, right? We started by going all the way in to where x was, and then working our way out. Well, I suggest that that's the best way of dealing with these guys here. We're going to do the same thing. Let's just, real quick, I don't want to lose this work. F of g of 4, we just found, we evaluated that works out to 2. So it's the same as f of 2. 3, okay, comes out to 3. All right, we'll use that in a second. So, okay. Now let's do the same thing, but only instead of plugging in a 4 to begin with, we're just going to plug in an x. So I'm going to say, start off this way, pretend I haven't written it before, and I'll say, okay, what is f of g of x? Now in this case, I'm not plugging in a number, so I can't get anything new out of it. It's pretty much we're done, right? You can't get any more information out of that guy. So what I could say is, well, that thing represents a formula, right? Well, it's a function. It tells me how to calculate the output. That thing means the same thing as that thing right there, so I'll just replace it. I'll say that means square root x. Now I'm going to say, okay, well, now what? Now I've just put something into f. What does f tell me to do? Well, f says to take that thing, okay, so I'm just thinking, like if I were writing this, I would say f of whatever equals whatever plus 1, right? That's what that means. So I'm going to say, okay, I just take that thing and plug it in right here. So when that's a root x, we get a root x right there. So this just turns out to be square root x plus 1. Okay, so then that is f of g of x. F of g of x, which is a function in its own right. Anyway, we'll get to that. Now, let's see what happens when I plug in a 4, right? If I had just given you this, if I just said, here's this, and now, like we never saw any of this at all. If I just told you that this equals that, and I said calculate f of g of 4, you would say, okay, wherever I see an x, I replace it with a 4. And so I'm just going to write this the same way I just saw it, and instead of x, I'm going to put a 4. Okay, and what would you do? Then you'd say, well, positive square root of 4 is 2. 2 plus 1 is 3. And hey, we get the same thing that we got before. So what we're doing is, it's kind of like we're doing the same thing that we did. We're saying plug a number into G, then take that output, plug it into F, and you'll get something new. But we're doing it symbolically. We don't have a number X, so we can't actually calculate it, but symbolically we can. We could say, doing this, right, having this new function, which maybe we give it a new name, maybe we call it big capital F of X. Now we have a function which you give me any input, X, and it does this thing to it. It's the same thing as doing G first, then taking that output, plugging it into X, and then getting that. But we have it in symbolic form. So that's all we're doing right there. Okay, let's do the same thing with G of F of X. I wonder if they're the same thing, right? A plus B is the same thing as B plus A. Maybe this works the same way. Let's find out. So, same thing. I'm looking at this and I'm seeing, okay, we have some stuff to calculate. It's the innermost thing. Oh, there's X. Okay, well, X is just a variable. It's going to come along for the ride. And so now, F of X is what? F of X means the same thing as X plus 1. So I'm going to say, okay, that's the same thing. The output of that is that right there. Okay, now we could say, well, G of something, that's the rule for that. Whenever I see that, I just put it right there. So that means I take the square root of whatever's in there, which happens to be X plus 1. Now, what happens if I plug in a 4 in there? Remember when I plugged in a 4 into here, I got 3. Now when I plug a 4 into there, I get, well, that would be 5, the square root of, the square root of 4 plus 1, which is the square root of 5, which is certainly not equal to 3, right? What we're seeing is, unlike addition and multiplication, if you do A plus B, it's the same as doing it in opposite order. It's the same as doing B plus A. This is not the same kind of thing, right? This says do G first, then do F, and you'll get this. This says do F first, then do G, and you'll get something different. And so that is what we're looking for right there. So that function, again, if we wanted to, we could give it a new name. We could call it big capital G, or whatever you want. And it's a function in its own right. It's a function where you plug in a number, you do that to it, and that's your output. And it's the same thing as plugging a number into F, taking that output, putting it into G, and then getting a new output out of G. Okay, now the next one. It's starting to look pretty terrible, right? Get rid of this. It's like, uh-oh, now we got a bunch of them to do, but we'll just do by the same principle, right? I'm just going to write down what we have. G of F of X. I'm going to kind of cheat here. I mean, what we should do is look all the way into X and say, okay, it's not a number, I can't just evaluate it, so then I have to use that symbol. In fact, we'll just go ahead and do that. Okay, so that's H of G of whatever that symbol F of X means. Oh, that symbol F of X means X plus 1. Okay. Now we're plugging something into G. What is that? Well, G says whatever goes into it, we get the square root of it. And so now you see I'm just working my way out the same way as if we had a bunch of parentheses and a bunch of stuff, and we have to do one little step at a time, and we're going to work our way out. It's the same principle at play here. Now G of X plus 1 is the square root of X plus 1. And at this point, let's just kind of stop and notice that right there, H of that stuff, is the same as H of this stuff, like G of F of X is G of F of X, and we've already calculated it. So we could have just skipped a step and said, wait a minute, that symbol right there equals that. And you see, yeah, that's exactly what we've replaced this with right there. Okay. H of square root of x plus 1. Well, H says you take whatever's in there, go 1 over that amount. So I'm going to say, okay, 1 over the square root of x plus 1. Right, there you go. And again, if we wanted to, we could call this some new function, h of x, if we were so inclined. That's the answer. F of h of g. Now, we don't have an h of g yet, so we're going to have to go through and do this. So instead of rewriting it, I'm just going to go ahead and do it. We're going to say, okay, g of x, all the way in, find x. There's x. Work our way out. We don't have an x. It could be anything, so we're going to have to use the symbol. G of x means square root x. So f of h of, now instead of g of x, we'll just use root x, because that is what g is. Now, h of that stuff. H says, again, I'm not really using my brain here. I'm just replacing symbols. Right? I haven't worked my way out, so I know that's still on the outside. H of root x. H says take whatever's in it, go 1 over it. Okay, so 1 over whatever's in there, I guess that's square root x. Okay. F of something. Now we've worked our way out, right? We've done G, we've done H, and now we're taking this and plugging it into F. And F says you take that and simply add 1. So we're going to go 1 over square root x plus 1. In order to find the domain for these functions, it'll be a lot easier if we first find the domain for these three functions. So first off, what's the domain of f? Well, it's all allowable input values. And, like we've already talked about, this is just a line, right? And so there are no restrictions on what we could put in, right? You could add 1 to any number. So all real numbers work for this guy. Negative infinity, up to infinity, we're perfectly fine. Now, the domain of G. You can put a negative number into a square root. It gives you a complex number, right? So we're taking the positive square root like that, and it turns out that this is 2 times the imaginary unit. The problem is, if you put in a negative number, you get a complex valued output, right? And we want to stick to just the reals. We don't want any imaginary numbers. So what we're going to do is restrict the domain that we could put in here, and we're only going to put in values into there that are 0 or bigger. Okay, now, just real quick, let's check that I can put 0 into there. What's the square root of 0? Well, I think it's 0, right? Because what this asks, when you take the square root of something, it says, what number times itself is equal to that thing? So you say, well, 2 times 2 equals 4, and so the square root should be 2, right? The positive square root. There's also a negative square root, but we're talking about the positive square root. So it is the case that 0 times 0 equals 0, so it is the case, right, just like that the square root of 0 is equal to 0. Perfectly fine. We have no problems plugging in 0. We do have a problem plugging in negative numbers. So if I'm thinking about the number line, we don't have a problem with 0. We don't have a problem with any positive numbers going into G. We can put 0 in as an input, all positive numbers up to infinity, and so we're leaving out all the negative numbers. This is the interval that we want, from 0 up to infinity, right there. Okay, so that's the domain of G. What about the domain of H? Well, let's see. What numbers can we plug in? When we're trying to find out the domain, I usually start with 0. And I see, oh, I cannot plug in 0 into H, right? That is not defined. So it's not an allowable input. Okay, so I'm thinking about a number line. I know I'm leaving 0 out. We are not going to use 0. What about positive numbers? Can I take a positive number? Yeah, I could take like 1. 1 over 1 is perfectly fine. I could take, in fact, any really, really small number, right? I could go 1 over a billionth or whatever. There's no problems there. I could take all positive numbers. I just have to leave out 0. What about negative numbers? I can divide by a negative number. That's perfectly fine. I could take 1 over negative 2 and get negative 1/2. That's perfectly fine as long as it's not 0. So in pictures then, we're basically the only number we can't allow is 0. So we're going to pull that out from the number line. And we're going to say, well then what's left over are these two intervals. Everything from negative infinity up to 0, not including 0. Union that with this interval, which is 0 up to infinity. And we're going to consider that as one set. That is the domain of H. So knowing the domains of these guys is going to help us figure out the domains of these. So if I consider this function, I'm just going to give it a new name. I'm going to call it big F of x. That'll help with notation a little bit. I'll say big F of x is that guy right there, x plus 1. Now, I want to find the domain of big F. And I'm going to say, okay, what are my allowable inputs? And I could see, well, the only problem you have here is that square root, right? And I know that whatever goes in there needs to be 0 or bigger. And so x, then, the thing that goes in, needs to be bigger than or equal to 0. And so, again, on the number line, this is exactly the same as the domain of G, right? We could say all numbers from 0 up to infinity. There you go. So that's the answer for the domain part of this guy. Now, what about for the next one? And again, I'm just going to use the same notation here and say, okay, this right here is a function of x. And so what about when that's the function of x? Same kind of reasoning. It's like, well, the only problem we could run into with allowable inputs is we know that whatever goes into a square root, whatever that happens to be, whatever we're putting in there has to be bigger than or equal to 0. Well, what is it that we're putting in there? Well, it's x plus 1. Oh, so then x plus 1 has to be bigger than 0. That's how I like to reason it out, right? We try to be all creative and be like, well, hold on, but if x is 0, then wait, no, but it's fine, so we could go. Don't they just do it symbolically and say whatever goes in must be strictly bigger than or equal to 0. And now we're back to like quiz 0 stuff. It's like, okay, now we need to write this in interval notation. And so that right there, right, I'm getting a relationship involving x. And I could say then you're at -1. It has to be bigger than or equal to. And so we're going to say we're including -1 all the way up to infinity. And so to write that as an interval, we're going to say all the real numbers from -1 up to infinity. Those are my allowable inputs to that function. Now let's just check it and make sure, right? Plugging in the -1 into there gives me -1 plus 1 is 0. That's perfectly fine. Plug in anything bigger and you have a positive number, so yeah, you're good to go. Okay. Now, for the next one, this guy, 1 over the square root of x plus 1. When I look at that, I'm thinking, okay, now we have two problems, right? One of these problems is the square root thing that we just saw before. And in fact, let's just go ahead and say, okay, from the work that we did before, we know that what goes in there must be bigger than or equal to that. But we also know that whatever this is, and look at how I'm thinking about this, just like last time, it's like whatever it is that we divide by cannot equal 0, right? So I'm thinking, whatever we are dividing by, whatever that happens to be, cannot equal 0. What are we dividing by? Well, the square root of x plus 1. There's a few different ways you could think about that. You could say, well then, what value of x would make that equal to 0? And we could think, well, it's -1. Or we could just say, well, especially if it's really complicated, like there's a bunch of stuff in here, it could be hard to see. And so I'm just going to treat this like an equation or a non-equation. That's fine, right? I'm just going to say, okay, how do I get rid of square root? Well, I guess I just square both sides. And if we haven't talked about that yet, don't worry about it. You'll be doing plenty of this soon enough. And we get 0 times 0 is 0. Something, a square root of something squared undoes the square root because square root and square are inverse operations of each other. And now we could just say, yeah, okay, subtract 1 from both sides and we get that x cannot equal -1. And as far as that guy's concerned, as far as the 1 over stuff is concerned, that's the only restriction. It would be fine if it were negative. It would be fine. I mean, it would be fine if it were on the other side of -1. It would be fine if it were bigger. But we also have this restriction right here, which we know from earlier that we have that. So this says that x has to be strictly bigger than -1, or it has to be bigger than or equal to -1. This says it cannot equal -1, and so we're going to have to say, well, we're going to have to drop that equality there, right, and just have that. And so that is going to determine the domain of this function. And so, let's say, all right, as far as a number line is concerned, you have -1 has to be strictly bigger, right? And so it could be anything out here up to infinity. And so as an interval, we have from -1 up to infinity. And so I'm going to say my domain of big F is everything from -1 up to infinity. But I'm going to check this, right, because we kind of combined two ideas here. And I'm going to say, what happens if I go just outside this interval? What happens if I do plug in the -1? Well, I'll plug in a -1. I get -1 plus 1 is 0. Square root is 0. Perfectly fine. Take the square root of 0 and it's 0, and can't do that. So yeah, I could see that this is all kind of coming together. I put this together the right way. So there you go. That's the domain for the function from f. Now we're finding the domain of this function from part G, which I've rewritten here as big capital F of x equals 1 over the square root of x plus 1, and we are trying to find the domain of f. Okay, well, I can see just by looking at this, there's only one place that could be a problem, right? And it's that guy right there, right? Because plus 1 is not a problem. The 1 on top is no problem. You can take 1 and divide it. It's fine. Problem, and it's, again, kind of like a mix of what we saw last time, right? So on one hand, so let's just break this apart, right? On one hand, the innermost thing, I'm looking at x, and then as I work my way out, I see square root of x. And so I know that that means, okay, x has got to be bigger than or equal to 0. And so already I'm thinking about this interval. Okay, we can include 0, and we're going up to infinity, so that would be the domain of that guy. But now, as I start looking on the way out, I see that, well, since it's 1 over that stuff, I know that whatever's in there can't be equal to 0. And so then square root of x cannot equal 0. And we've done this before, right? That means that x cannot equal 0. And so in that case, we have to get rid of the one place on here where it does equal 0. We get rid of the 0. Another way we could say that is we're going to exclude 0, right? And we get this interval, everything from 0, not including 0, up to infinity, like that. And that is the domain of f in interval notation. And so that's the domain for that part right there. So for parts I, j, and k, I ask you to find an inverse function for the given three functions f, g, and h. Now, to find the inverse of a function, I've broken this down into 3 steps that you're going to do almost every time. Let's kind of pick apart why we're doing that. Let's think about what the inverse of a function is. First off, you have a function f that we've defined, right? And if we've defined it in terms of x, this says you take an x value, I'll tell you how to compute it to get a y value. This is the kind of thing we draw. We draw this thing to represent f, but it's just a map that tells us basically where to go. It says if you're here, if your x is here, you choose this x, this map tells me, okay, then I need to go here to y to get the output. Now, the inverse is just the opposite game, right? It's like, well, if you were at y, then we would have to come back. We'd reverse these arrows. We'd say, if you're here, you go here and come back to x. That is, plug in an x into the original function f, and you get out a y. What we're looking for then is a formula that tells me, and we call this formula f inverse, formula that says, well, if you have a y, that y, we need to find out where it came from. We want x as the output of that. And so if f is defined by a graph, there's a way to do that. If it's just a relationship, like with arrows and stuff like that, then we do it a different way. But when it's given by a formula, like these guys are given by formulas, then what we're going to do, we're going to follow these steps right here. Because remember, the goal here, right, when I say write what that is, I'm saying you give me a formula that I could use to calculate so that it undoes what f does, right? So, okay, we're on the same page there. Let's look at these steps. So first, I've written write y equals f of x. So we're going to find the inverse of some given function f. And notice I've written f of x. This is assuming that your input value is x or z or t or something that's not y. The important point here is I don't care what symbol you use to be the output value, as long as it's different from the input value. That's going to be very important that we do that. So let's do part I. We are looking for a formula for the inverse of that. So step 1, we are just simply going to write y equals f of x. And in this case, f of x is x plus 1. So I'm going to rewrite that y equals x plus 1. Okay, step 1 is done. Now, step 2, solve for x, or as I like to think about it, get x by itself. And so I look at x and I see, okay, what's happening to x? Well, x gets 1 added on to him. So I'm going to subtract 1. That kind of makes sense. I mean, I'm undoing, if f is a rule that tells me what to do with x in order to get a new output, I'm really just, if I undo that, then I should start back off where I began, right? So, okay, now we have y minus 1 equals x. Okay, we have solved for x. We've gotten x by itself. Okay, well now, this right here, this is that formula that you're looking for, right? That is, given any output y, how I had it before, given any output y, this tells you, this formula tells you how to find the original input x right there. So then that's the formula that we want. So we can write that as f of y, f inverse of y equals y minus 1. Now, before we move on, let's just check that this is truly an inverse, okay?
Now let's do this graphically too. I want to really drive this point home. So the same picture we had before, only now we don't have just some squiggle. We actually have x plus 1. We know what it looks like. It's a line. It goes through here at 1. And let's just choose a point. How about we plug in a 2? When I plug in a 2 for x, my output is going to be this number. Well, let's see. If I plug in a 2, plug in a 2 there, I get a 2 there. Plus 1 is 3. Okay, so we're up at 3. That's my output. Now let's check that when I plug this in for the inverse, that it does give me back the original thing. And we hope so, right? So f inverse of, we'll just kind of write it without the variable here. Say, okay, whatever I put into there goes right there. Okay, whatever I put into there goes right there. So when I plug in a 3, it says 3 minus 1. 3 minus 1 is just 2. And indeed, this is the formula which gives me back the original input. And so I have a formula which gives me back the original input, and we should be done. The only problem is I did not ask you to write a formula for f inverse of y, which is what we have here. I said I wanted a formula for f inverse of x. I'm deliberately being tricky. The reason why I'm doing this is because almost always our functions, when we write out a function, what's the input value? It's almost always x, right? And that's just kind of one of those conventions, especially when your numbers are real numbers, inputs, your input numbers are real numbers, you almost always use x. And indeed, all of these functions, their inputs are real numbers and their outputs are real numbers. And so the inverse function is a function in and of itself. This is, if I had just written x minus 1, that would be a line. It's a perfectly good function. And since its inputs are real numbers, we usually think about that. We usually write those as x to begin with. So the final step is, if necessary, rename y. And so I'm thinking, is it necessary? Well, yeah, it doesn't say to plug in a y, it says to plug in an x, whatever that means. And so the final step would be that right there. I'm just going to, everywhere I see a y, I'm just going to replace it with an x. Okay, now, real quick, I would just like to check that this thing is the true inverse of this function. So what I'm going to do is say, all right, let's think about this. When I plug in an x, I get out what we call f of x, right? F of x. We call it y. We've been calling it y, but you think about this as, in symbols, f of x. So that's the output. And so then what we've just said here is, if I then plug this into that function, right? That's what we did. We had the y value here. We said that this thing is equal to y. And when I plug that thing itself, y, into the inverse, we should get back to where we started. So let's check and see if that's true. What I'm saying in symbols here is, if I take this and plug it into this function, what would that look like? Well, we've been doing composition of functions. We say f inverse of what? Well, of that, whatever it is, f of x. And what I'm saying is that this thing should, if I started with x, plug that in, right? Push that forward, and then I pull it back with this guy, I should end up where I started, right? I should get an x as my output. Let's check. Like we've been doing with all those compositions, I'm going to say, look in the innermost thing, what is f of x, and replace that. Let's say f inverse of, well, f of x is just x plus 1. Okay. F inverse of x plus 1 1. Well, f inverse says to take whatever the input is and do that. So I'm going to say, okay, f of x says take whatever the input is and minus 1. What was the input? X plus 1. X plus 1. Well, that's just x plus 1 minus 1. Plus 1 minus 1 is a big fat 0, and we're left with just x. And so we do, right, I'm asking, is this true? Is this true to begin with? And then so I just evaluate it out and find, yes, indeed, that does equal x. That should be an inverse. However, we're not done. And we'll see this with harder problems or with more sophisticated problems. Not only does that have to be true, remember what I just said? Like this is kind of a function in and of its own right, right? As a matter of fact, we could think about it. We could go ahead and just graph it and say, all right, what does that thing as a function look like? Well, it's x minus 1. And so it's just a line. It goes through here at minus 1. And it has a slope of 1. Okay, so it looks like that. And now we're going to say, okay, if I take any x and plug it in, remember this is f inverse, plug it in, I get some output value. So this function is f inverse x. And when I plug in that x right there, I get f inverse of that x. But since this is the inverse of it, remember what we just did, right? Like if I then push that forward with f, if I plug it into f itself, well, I should get x back, right? So let's go ahead and check that that's the case. What I'm saying is so in here we have the inverse of x. So it's like I had some output from my original function. Now I'm saying, where did it come from? I find out where it came from. And then I push it back forward. Well, we should end where we started off, right? It makes sense. Inverses of each other are inverses of each other. It doesn't matter which one I call the inverse. They're both inverses of each other. So this should work. If I plug in an x and then do the inverse, and then I do the function, I should end up right where I started. So let's check that that's the case. Okay, all the way in. What is the formula for that? With x minus 1, okay? But then what does f say to do? It says to take x plus 1, or whatever's in there, plus 1. So whatever's in there, plus 1. Those guys cancel out. And I'm left with just an x. And so indeed, we're asking, is that true? Yes, it is true. We are good to go. This is the inverse of f, written with x as an input. And we're going to find the inverse of g. Okay, so what do? We have a formula, and so we're going to write y equals g of x. It doesn't matter what letter I use as long as it's not the same as the input letter. Okay, so we have different letters. That looks good. And I'm going to say, okay, y equals square root of x. Now, real quick. Square root is the inverse of square. Like if you square something, you're asking, and you take a square root, you're asking, well, what was it before it was squared, right? Like, for instance, the square root of 4 equals 2 only because 2 times 2 is equal to 4, right? Like that's pretty much how square root is defined, right? So just take a second here and think, well, if we have something like this, the square root of 4 is 2. What did we just do here, right? We just said 2 times 2. So let's do that and say, well, wait a second. Instead of writing 2, you told me the square root of 4 is equal to 2. So I'm just going to write the square root of 4. That's the same exact thing as 2. I take the square root of 4. That's the same exact thing as 2. And so what we're seeing here, and this is how I think about it visually, is like whatever number is in there, the way to make it pop out, right, is to take this thing and multiply it by itself, right? So in other words, when you square this thing, whatever that square root something is, when you square it, it makes whatever is in there pop out. So if I had started with say a 25, we would have had a 5 times 5, which would be the square root of 25 times the square root of 25, right? And so indeed, like I could have replaced all of this with, well, whatever this is, we don't quite know what this is, but we could say the output is X. Well, then for this to work, that has to be that right there. Right, just in symbols, this is all I'm saying. Okay, so just by the way we've defined square root, you may not have been aware of this, but you've defined it as an inverse function already. The inverse of a function that you're familiar with, kind of, which is take something and square it. So we're about to see that that's the case. So what did I say here? When we take this thing and multiply it by itself, it makes that thing pop out. That's how we undo square root. So I'm going to go ahead and take this thing and multiply it by itself. But whatever I do to one side, I got to do to the other side, right? I could say, okay, well, I'll have to square this side. And when I do that, we get y squared is equal to, the whole reason I did that in the first place was to make the x pop out. In other words, to get x by itself. That's what I wanted. I wanted x all by itself, and now I have it, so part 2 is done. Now, over here, I have a formula. I have a formula for the inverse in terms of y. So g inverse of y is equal to y squared. Okay. Okay, are we done? Well, technically, yeah, but if necessary, we need to rename y, and it is necessary because I asked you to do it in terms of x. So I'm going to say, well, wherever I see a y right here, I have to do that to it. So if I wanted to plug in an x, I would just replace this like that. Okay, so that's our answer, but now let's check it. Let's check our answer. Inverses, when you compose them with each other, right, they need to give you back what you started with. So let's take the inverse and then we'll push it forward with g, right? So visually, what we're doing here is we're saying there's some function, f of x, and we are, first, we're going to have some output here. We're going to pull it back with the inverse, right? We're going to take g inverse first, and we'll get that number. That's what that means right here. We're saying take that number. We're calling it x. Sorry, it's on the y-axis, but let's just open our minds a little bit and say, yeah, it could be named x. That's fine. We're taking some number x, pulling it back with the inverse, right? And then that is what you get right there. That's what that is. This is g inverse of x. And then we're saying, well, now just plug that bad boy into g. Plug that into g, and you should get g of whatever that thing is. G of that thing is g inverse of x. And so that's what we're checking right now. We're just saying if you started up here with an output of g, pulled it back, and then pushed it forward, you should end up where you started. So let's check that that's the case. Should be fairly easy to check. So we're going to say, okay, looking all the way into the innermost part where the x lives, and we'll say, okay, well, x is just a variable. We can't rename him, or we're not substituting him with any kind of value. And so that right there, we have a formula for it. It should just be x squared. So g of x squared, like that. But what is g of something? We've defined that to be the positive square root of that something. Well, by definition, that is exactly what x is right there. Okay. One thing to notice, well, we won't worry about that too much. We'll get into that later. So that way works. Now let's go the other way. Right. We'll start with g this time. So back to our picture. We have some function g. And now we're going to start with x right here and say, okay, push him forward first by plugging him into g, and you get g of x. Now, if you take that and pull it back, if you plug that value into the inverse, what we should get is right back to where we started. So we're going to take that value, plug it into here, and we get g inverse of that value. G inverse of g of x should come back to where we started. That should equal x. So let's do that. So g inverse of g of x. All right. So looking at the innermost thing is an x. Now plugging in value in, so he's staying alone, moving out g of x. Well, we have to use the formula. So, okay, g inverse of g of x is the square root of x. Now, what does g inverse say to do to it? It says take whatever's inside and square it. Okay, so I'm going to take whatever's inside and square it. What's inside? That's the square root. That's the square root of x times the square root of x, which is just x. So we found a formula for the inverse, and we've checked that when we do it in both ways, right, g of x and then g inverse, or g inverse of x and then g of x, we end up right where we started with this x. So that is good to go. Finally, we need to find a formula for the inverse of h. Okay, so we're going to write y equals h of x. Right, now let's replace h with a formula. Okay, now it's like, well, what do I do? Well, we have to solve for x. Let me get x by itself. Whenever I see fractions, I get a little like, wait, what? And it can be kind of hard because you think about it as get x by itself, you're like, x is by itself. It's all by itself. Yeah, but something's happening to x, right? We're not saying it's not x and then divide by 1, it's 1 and then divide by x. And so it's weird, right? So what I like to do when I'm in this situation, I kind of ask myself, what's messing up my life right now? And that answer is, well, there's a fraction, right? Whenever there's fractions, I just think, man, if that fraction weren't there, I'd be a lot happier. Well, luckily, there's a way we could kill a fraction pretty easily. You could just say, well, fraction weren't there, that would be nice. So what could I do to get rid of the fraction? Well, I could just multiply by whatever that denominator is. I don't even need to think. It could be any fraction, like, I don't know, 75 over d plus 1 squared. And I'd say, well, how do I get rid of that fraction? You don't have to think about it. Just multiply by whatever that is, in that case, d plus 1 squared, and it's gone, right? That's how we kill a fraction. So let's kill that fraction. We're going to say, all right, x is in the denominator. To get rid of it, I got to multiply by x. Whatever I do to one side of the equation, I got to do to the other side of the equation. That's so we get that. Okay, so now we have x times y is equal to, oh, that's why I did that. Now it's gone. I don't have to worry about that fraction anymore. Nice. All right. My goal was to get x by itself. All right. X is not by himself. X gets multiplied by y. How do I undo multiplication? Division, right? So I'm going to divide both sides by y. doing that cancels the y's on the left, or y divided by y is 1. Divided by y. And there we go. Right? X is all by itself. That right there is a formula involving y. And so right there, that is my formula for the inverse. Okay. Finally, if necessary, rename y. I look over here and see, yep, my input values to the inverse are supposed to be x's. So I'm just going to rewrite this, and I'll go this way. H inverse. Instead of a y, I'm going to put in an x, which means I need an x right there. And good to go. Hey, interesting. That's what we started off with. Huh. I might now, honestly, if I were doing this and I had never seen this before, I would think, wait a minute, something's wrong here. I must have done something wrong because I ended up with the same function. How could a function be its own inverse? Let's just check. Let's just check and see, right? This is why I go through how to check these things, because you're going to run into things that just don't feel right. I don't know about you, but this doesn't feel right to me. So one way we could check it is to check the two compositions. We could say, okay, if I take H inverse and plug it into H, I should end up where I started. It should be like that, right? Okay, what's H inverse of X? Well, we have it written right there. So I'm going to say, okay, H inverse of X is the same thing as 1 over X. Okay. So now let's see, H says to take whatever's in it and go 1 over it. So I'm going to say, all right, that's the same thing as 1 over whatever that is. Well, that's a fraction. So I'm going to use some parentheses so that we can make sure we haven't messed anything up. Yeah, we take H of X says to take 1 over the thing. And so this says to take 1 over that, 1 over that. Now I remember the rule for dividing by fractions. It's the same as take whatever's in the numerator, which happens to be a 1, and multiply by the reciprocal of that thing, which is x over 1. 1 times x over 1 is just x. And we're back where we started. So it is the case. We were wondering, is that true? It is the case that h of h inverse of x is just x. And you can kind of see it now, right? Like, yeah, this says if I plug in a 2, I get 1 over 2. And then this says to undo that, I go 1 over 1 over 2. 1 over 1 over 2, that's the same as 1 times 2 over 1. Oh yeah, and you're back where you started. Okay, that makes sense. What about the other way around? Well, if you've already beat me to the chase, you could probably just skip or just stop watching the video right now. Let's just check the other way around. Let's say H inverse H of X. So we do H first, then we do H inverse, right? What does that say to do? Well, H inverse, I'm sorry, H of X is 1 over X. So we get that right there, right? Oh, it's the exact same thing. We just did this. Like I said, if you want, if you beat me to the punch, go ahead and stop right now. But right, so H inverse is the same thing as H, and so we get 1 over X, and we're right back to where we started. It is the case that you will end up where you start if you do that. So this is the inverse of that function right there, and there's your answer.